It must be a busy exam week. We've got about half the number of people, or maybe less, than we normally have here in class. And there's been some asking for extensions to the deadline for homework too. So I asked the TAs about this, and they were behind pushing back the deadline for the homework. So so I haven't done it yet on Canvas, but we'll move it back, and I guess we'll just move it back till after the break, so you could have the break to do it. But if I were you, I would do it during the break. So I don't know when you're going to do it, but if that seems helpful, that's what we'll do. Any questions before we get started? Any questions about homework or anything like that? Besides extending the deadline?
I have a question about padding.
Padding, yeah.
How do you decide how large the padding is?
Yeah, the typical thing you want to do is you want to take so it depends on the filter size, right? So you take your filter size and you put it in one of the corners of the image, and you say how much padding will I need until this image now fits in to the expanded, the padded image. And so if you're 3 by 3, that's going to require one row and one column row of just one padding of 1, right? Because then that way that image will fit in entirely. And if it was a 5 by 5, you need 2. If it was 7 by 7, you need 3, and so forth.
So in PyTorch, when you pass in the padding parameter, so the number is how big the padding is, right?
Yeah, so it's the number of pixels you're adding around the image of zeros. Yep. Okay, any other questions? All right, well, we'll get started then. So we finished our history lesson of, is that kind of hard to see with that light on right there? Seems like it to me, just this one right here. I'll probably not figure it out how to turn it off, but yeah, can't do full.
Is the other TA here for that? No.
We gotta go
on Thursday.
Okay, so we finished the history lesson of convolutional networks using the ImageNet competition. We went through a lot of different networks. Again, the standard ones that you're going to see in most model zoos in libraries like PyTorch and TensorFlow. This was all about classification. We've up to this point we really focused just on classification, determining which object is in the image. And the ImageNet 1000 classes is set up for that. But there's a lot of other things that we might want to do in computer vision that are related, but require different kinds of objectives and also architectures. And so that's what we're going to try to talk about today. So we're going to move beyond classification. We're going to talk about the task of detection and segmentation. So this is what we have been doing. But what we want to do are some of these other really cool tasks. So for instance, semantic segmentation. We'll start talking about this first today. The semantic segmentation is where you basically want to classify each pixel in the image as being part of an object. And so, look at this image right here. You basically want to say, okay, for all each pixel here, what general object is a part of? And you can see how this has kind of been. Think about this being laying on top of this. The pixels, or most, more or less, the pixels associated with the cat are labeled cat. Those associated with the grass are labeled grass. Those associated with trees are labeled trees, sky, and so forth. You can imagine doing this for all sorts of interesting, kinds of tasks. This is a task known as semantic segmentation. We want to be able to, for each pixel in the object, sort of say what object it's a part of. Another task is this task of localization. So being able to basically within an image draw a kind of box around the object that's there and then classify it. So we've been doing this, like, you know, we can use the kinds of architectures that and like a cross entropy loss to be able to say that there's a cat in this image. But this, in addition to that, says there's, you know, it says like, hey, there's a box here, and inside this box there's a cat. So it's a little bit more detailed. You know, it's a related task, but more detailed. Like, for instance, the network's going to have to draw these boxes. You know, how do we do that? So that's kind of the stuff we'll talk about today. We might actually have multiple objects within an image that we'll want to detect. We want to be able to detect each one, and again, say what kind of object is in there. So in this case, we might have 2 dog objects and a cat, and then, you know, this could continue, right? Like, this is kind of simplified. We might be able to say that there's a tree back here, maybe a couch over there, a pillow, whatever. Just kind of depends on your training data, how you set the task up. And then finally, just a refinement on that is doing the very same thing, but instead of giving you these bounding boxes, you actually say, like, within that bounding box, what are all of the pixels associated with that object in the bounding box. And that's a task known as instance segmentation. Okay, so like these are other computer vision tasks, and basically, you know, the things that we learned so far, like convolutional neural networks, are going to be a part of how we're going to go about learning to do these tasks. But we're going to have to basically like change the losses, right? Like we're not going to be able to have this straightforward cross entropy loss for doing kind of straightforward classification, but we're going to need to be able to say, you know, produce these. In this case, they produce these bounding boxes, then say what's inside of it, or produce a mask for the bounding box that tells you which pixels are part of which instance. All right. So yeah, so we're gonna do these things today. Note that you know, very often when we're looking at images, we often kind of simplify things and draw like 2D detection boxes, you know, these bounding boxes. But you know, obviously we live in a 3D world. These are just kind of 2D projections, these images, and we could, if we have the right training data, we can learn to do even more complicated tasks like drawing 3-dimensional bounding, not boxes anymore, but these bounding like prisms around these objects. So it's not, you know, it's not too different. Like that task is not too different from this task. Here, basically, you need to produce, you know, basically the coordinates of a corner and then the lengths to go in the bounding box, and then you have something similar here where you need to produce a corner and then the lengths, not just in 2 directions, but a 3rd direction as well. So, you know, the tasks are very similar to each other. Again, this is going to depend on the kind of training data you have. You have to, if you want to learn to do 3D object detection, you're going to have these, you know, 3D boxes, prisms drawn around your objects. But, you know, the approaches will be basically the same. So let's get started and start thinking about how one goes about the semantic segmentation. So before I even start here, I make a thought about what we're going to do here. What's the task? The task is at every pixel to say what like object or class it's a part of. You're going to make a suggestion?
No.
Oh, yeah.
I thought you were asking questions.
I was asking a question. Yeah. So how would you do that? Like, how would you approach this?
Basically, do classification but for each pixel.
Okay.
Yeah.
Yeah. So
Pixel 1 is without the 1.
Yeah. So instead of there being just one like classification loss term, we now will have one for basically all the pixels that we would optimize altogether. Yeah, that's the basic approach here. That's right. The question is like, how are we going to do that? Because what we've been doing so far is that we've been learning networks that like take your full image and like you can think of it as like compressing it down, right? Like you know, we're learning useful features for doing the task, but as we've been doing that, we've been compressing that image, we've been reducing like the spatial extent of the feature map, maybe typically gaining like in terms of the adding a lot of channels as we go, or like each one. Remember I said at some point, think about each one of those as like as an independent feature. We've been adding those channels in the feature map, but we've been compressing. But here we had like for to compress, like how would we take that compressed feature map and then say something about all the pixels in the original image? So we need to kind of think about how the architectures are going to change to accommodate for that. Yeah. So how do we go about it? So there's a kind of naive way to think about this, and that is to just like to train a classification model that takes these, but basically just takes like some sort of patch size. You can figure out how large. I mean, that might be a hyperparameter, and basically you would train it to take this patch and then train it to tell you what the class is of the pixel in the middle of the patch, of this kind of crop of the image, right? So the way this would work is what's in the center here. Well, this is part of the cow. This one's also part of the cow. This one right here. Then the center is the grass. Even though there's some cow in there, it's the center picture of the grass. And so you could just kind of like you could train this thing. You could just kind of randomly take these crops. You'd have the labels. Again, you'd have to have a training set where every single pixel is already labeled, so there's a bunch of work to do there. But once you've got that, you can do this, right? And then at inference time, you basically just have to run a forward pass over each patch in the network. Obviously, this is problematic. This is like really, 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 really inefficient, especially at inference time, where you're going to have to run so many forward passes for a single image. And also there's a lot of correlated data here, right? Like you take one patch and then you move one pixel to the right or one pixel to up or down or whatever. Like typically, like that's going to have the same. More often than not, that's going to be the same class. I mean, sometimes it's going to change, obviously, when you cross boundaries and things like that. But this is like super inefficient. So we can do better. So how do we do better? So the idea here is to have convolutional networks that like basically remain fully convolutional. So when we've been doing the standard classification task, we've been compressing the networks, and then those get eventually those get turned into a vector of length whatever. There might be a few fully connected layers that get you to a vector of the length of the number of classes. Those are your scores. You feed that into a soft max. You feed that into cross entropy loss. That's your signal for training the network. Here we're not going to do that. Here, the basic idea we want to have is to preserve some kind of preserve like the spatial extent in some way. And then when we do argmax, we're going to basically do argmax. Like we're going to do this until we get a feature map that has the same spatial extent as the original image. Okay, that's what this h and w here, the height and the width. And the number of channels is the number of classes, right? And so the way you can think about that is that there's a vector of length c, the number of classes at every single pixel, and then that you'd run your softmax and have your loss applied at each one of those pixels. So this is like the basic idea. There's only like one kind of small problem. Anybody see it? You see it now that I've been there? Right, like one of the reasons why we were doing this, like reducing of the spatial extent of the images, is that like this becomes really expensive. The convolutional operation is quite expensive on like large spatially extended feature maps. And so we were gaining some computational efficiency by reducing that size and forcing the network to learn good features at each of the smaller spatial extents. So, you could set this up, but you wouldn't have a very deep network because you just have so many operations as you move from layer to layer. If you don't still somehow reduce the spatial extent. So what's the solution here? The solution is to do what we've been doing, reduce the spatial extent of the feature maps, but then turn it around. Everything's still fully convolutional. We haven't like collapsed down to a vector only, right? So we still have the spatial extent, and then kind of go backwards. Like instead of this downsampling, we want this kind of upsampling until we get back to the original size of the image. Yeah.
So in that case, like, how would we do it? Like, is it like a stride of 1/2 then?
Yeah, that's not a bad way to think about it. We use a kind of we use what are called transpose convolutions, and that's what we're about to talk about. Yeah, so we know how to do downsampling, pooling, stride convolutions, or stride greater than 1. How do we go back the other direction? So, just some naive ways to think about this, right? You want to go from like, spatial extent of 2 by 2 to like 4 by 4. You could do this kind of naive thing where you just replicate the value in each of these like quadrants, so to speak, or in each of these pixels into the like corresponding set of expanded pixels, right? So like we're doubling the size here. So for every pixel here, we want to get a 2 by 2 output, and we can just replace it with that. Another way to think of this is you could just get your 2 by 2 grid for every single one of these, but only everything is zeros except for say like the top left entering the grid, or pick whatever grid you want. As you might imagine, like these aren't great. There's really no learning going on here. There's just sort of just a spatial expansion without there really being like a kind of a learning of how to go from low resolution to higher resolution. These were different kinds of unpooling. One thing that is sometimes used or was used more often in kind of older fully connected networks was to have like wherever there was a pooling operation, to have there be like an unpooling operation. So if you're doing max pooling, then you would do max unpooling, and it looks like that kind of what was like in quotes this bed of nails thing, but the position you put it in is like you remember where the max was, and then you put the corresponding thing back in there. Sometimes this actually is used in some architectures, like early fully connected architectures, but usually you wouldn't see it anymore. But like somehow this was like a good idea, or like it seemed to help anyways, like empirically. So the real thing you want to do is you want to learn to do this upsampling. This is what's called transpose convolution. So just to motivate this, remember what we're doing here. If you have a 3 by 3 convolution, stride 1, pad 1. Again, it's pad 1 because it's 3 by 3. To fit this thing in the corner, you would just need to add another pixel worth of zeros. Right, and then as we slide this along, we get our entries in the output. We have a stride 2. We get something smaller. So we kind of want to reverse this operation, and it's called transpose convolution. I'll motivate that a little bit later, like why the word transpose. But the idea here is simply to go, okay, well, for each one of these, I want to learn a filter that allows me to go from you know, one entry to, like, say, a 3 by 3 entry, or whatever the size is you pick. And start to fill out, from a single entry, fill out more of these entries. One question that comes up really, you know, so like how we do that exactly, we'll talk a little bit more about it, but like, one thing that comes up immediately is that, you know, you're going to start to get these overlaps. What does that even mean? Well, if we're producing numbers for, you know, from one number here, we're producing, say, like, you know, 9 numbers within this 3 by 3 grid, and we have this overlap. Wherever there's any overlap, I'm just going to add all those things together. That's just like a standard kind of practice here. Right? You could imagine doing other operations, but this has a nice mathematical interpretation that I'll show you in just 1 second. And that's really simply it. Like, you're literally learning to, like, fill in these entries by learning weights here and doing a very simple multiplication of the filter weights by the number here. Just notice transpose convolution also has, like, a whole bunch of other names. Sometimes called deconvolution, but that's a bad name for it because it's not really deconvolving, even though maybe it sort of feels like that's like an opposite operation. Up convolutions, kind of coming to what you were saying about, you know, half strides, fractionally strided convolutions. It's actually, you know, when these things were starting to be introduced, somebody introduced, you know, had a paper where they called it this and used ideas of, like, going by 1/2, but it's not a typical way to refer to it. Backwards strided convolution, whatever. You'll typically hear these called transpose convolutions or up convolution. So how does this work? Here's just like a simple 1D example. For every filter that we're learning, we're just taking this entry, we're multiplying the weights in this filter by that entry, and, you know, we're putting it in to some, you know, as a some format, depending on, like, you know, how strided this is. Then we take the other number, you know, another number. We'll do the same thing with that filter, and then again, wherever there are overlaps, we're going to sum the entries in that overlap, and that's going to be the output as we do the forward pass for this this transpose convolution.
Don't we need to divide by 2 for the middle one, for the sum?
There's no divide by 2. No. I mean, even if it feels like you should have something like that, you remember, like, you're learning weights here, so like that can just be absorbed. Like constants like that can be absorbed. So it turns out, like, again, this is just like in the one-dimensional case, but you can imagine this happening. You can if you knew something about tensor operations, you could express this for the actual 2D example. But convolution like can be expressed as a matrix operation, at least 1D convolution. And here's what you have, right? You have your parameters. Sorry, these really should be z's right here. This is just a mistake in this. So that's what the z's are over here. It's just obviously it should be x, y, z. But so you have your data, you have your weights, and the operational convolution can be expressed as nothing more than a matrix multiplication here. And really, like, where the convolution operation is coming in is just in the shifting of this, you know, as we work our way row by row. And naturally, what you're getting is the multiplication of entries and weights, and then the addition of those. So it's exactly like the operation that we normally think of it. Oops. Oh boy. And now, why transpose convolution? Well, this upsampling can really just be expressed now by taking the transpose of, you know, this data matrix here and doing the same matrix multiplication. And the operations are all preserved exactly the way that we just described them for transpose convolution. So this is why it's called transpose convolution. it really comes from some mathematical, just the consideration of mathematical operations going on. Again, this is just in the 1D example because you can write it down easily. But hopefully it motivates for you, 2D and beyond. Okay, so yeah, and this is what it looks like for stride 2. Stride 2 because of, instead of just moving ahead 1 here, we went now moving ahead 2. All right, so here's your transpose. Okay, so like now that you have that operation, it's kind of very, very simple, but it's a way of learning how to go, how to go from smaller spatial extents in your feature maps to larger spatial extents in your feature maps in a learnable way. And that's what we do. We basically do that. We compress the signal, so now we can have more layers. Then they come back. This is showing it being very symmetric. It doesn't have to be symmetric, but like again, you're making all kinds of architectural decisions along the way. Sometimes you simplify these things by doing like symmetry, and there's like some reason for this. The extensions of this idea, like things that like called UNet that you might end up using like in a project. They're very common in like these semantic segmentation tasks, and like they'll create skip connections from matching layers in a kind of symmetric downsampling and upsampling. Doesn't have to be that way, but it's often done that way. And most importantly, your final feature map here just needs to have the same spatial extent as the original image, and then as many channels as you have classes, because then that you're going to interpret again like the vector of length c at each pixel as the scores for doing the classification problem at that pixel. Okay. Questions? Fairly simple, right? Pretty simple extension of what we've been doing, and this plus advances on these kinds of ideas are used all the time to do this kind of work. All right. So, yeah.
Do you know if people have tried stereo vision segmentation before? Because
Stereo vision?
from my point of view, it looks like if we have two images, like two eyes, then doing segmentation would be much easier because you can have a cause of depth, you can segment down the object very easily. So do you know if people have tried?
I mean, I don't, like, nothing comes to mind of like the projects that I know of, but like I'm sure people have done a ton of work in that. That would be for like a very specific kind of setup, like I don't know, maybe like a humanoid robot that has that's got like a kind of what do you call it, binocular vision, right? And learning, like maybe learning depth from that, something like that. I don't know off the top of my head like what those examples are, but I'm sure there's a ton of that. Somebody in here might know it. Cool. All right. So good. So that's the basics of semantic segmentation. So now 2D object detection. So the idea here is that we want to, so remember up to this point, it's been like, basically the assumptions there's one object of one class in the images, and you're basically classifying the whole object as having that image, or having that object in it. Now we're going to be a little more realistic about things and say, well, really, the way most images work is that there's a lot of different kinds of objects in there. I might really want to know where all of those objects are and what they are. And so that's the task that we're going to go on here, this multi-object detection. So drawing bounding boxes around objects, and then saying within that bounding box what object is there. Okay, so the basic idea here is that we're gonna, it's almost classification again, except for we need to produce these coordinates. So the coordinates for the box. So we can use the same types of networks, but instead of there just being a vector from which we learn class scores, we might want to, from that same vector of scores, or maybe from an earlier part of this network, have an additional head on the network that basically is doing a regression problem and learning what the coordinates of the bounding box are. So you need to know. So to draw a bounding box in 2D, you're going to need to know the coordinate of like one of the corners, typically the top left corner, and then the width in pixels and the height in pixels of that box, right? So there's basically 4 parameters that need to be learned here. So if your data has those bounding boxes already on it, those the corner and the width and height are now additional labels in addition to the label of the class, and now you have basically 2 objectives that you're trying to optimize at the same time. To do the classification within that box correctly, and then produce that box. So, but then again, we also want to do this for so we have the 2 losses, we add them together, and we have this multitask loss. A good point here is that very often this task is learned as like what's called a transfer learning problem, where you might train, say, your AlexNet or your VGG or your ResNet or whatever to do the ImageNet classification task, and then fix all of that, add some like net to your backbone with the different heads on there, and basically use this to give you an embedding or a featurization of your image, and then from there learn to do the classification and the bounding box task. I mean, you can learn it all end to end, which you end up doing for the more advanced models, which I'm about to show you. But in general, like, this is not a bad approach. Works quite well for obvious reasons.
But like one loss might be in some order of magnitude larger than the other loss, and it might dominate, right? So
That's a great point. So when you bring these 2 losses together, there's a hyperparameter, right? So like you're gonna have loss. Think of it as like loss 1, so call it like the softmax loss plus beta times loss 2, where beta now is going to be a hyperparameter that basically you can tune using cross validation. But a basic idea is that you want to bring it on the same scale as the other one if you want both losses to contribute equally to training the model. There might be some preference for, like, say, getting the classification, for doing better on the classification task while maybe not doing so well on the bounding box task, because maybe you don't care so much about the bounding box being exactly right, but you really do care about getting the classification of the object right. So you might actually use that hyperparameter beta to then to allow the loss to be more dominated by the classification loss than the regression loss. But that would be a decision that you would make as the person training this. But yeah, it's an excellent observation, and glad you asked the question. Okay, so trick here though is that if you want to do this for multiple objects in an image, there's going to be a variable number of objects in the image. There's not going to be a fixed one, right? Like just illustrated here, there's like 1 cat, 3 animals here, a whole bunch of, actually looks like geese to me, but it says duck, but whatever, like a whole bunch of these other animals. And when a priori you don't know exactly how many there's going to be. So you need to have, there needs to be some flexibility in how you're going to do this. And so what we're about to go through is going to show you how people thought about this problem and kind of iterated until we got to a really fast, accurate way of doing this. All right. So the not so smart way, but would work, is to kind of do what the not so smart way was in the segmentation, or the semantic segmentation task, and that is to take a whole bunch of bounding boxes of a whole bunch of different sizes, and then just start running them around the image, trying at each point here to say what's in that bounding box, right? So if you have if you have the appropriate data for doing this, then you might be able to you might know that you have 1,000 possible different classes, and you might try to classify the possible different classes, including some sort of null class, saying there's no object in this bounding box. And you could do that, right? It would work. But it's problematic, in the ways that you would imagine, because what's the right way to go about picking the right bounding box sizes, moving them all around? Yeah, how do you know how do you ensure that you have you don't have two bounding boxes that are classifying the same thing? I mean, there's a whole bunch of possible problems here, and obviously this is super expensive computation. So again, it would work, but there's probably better ways to do this. Sure enough, there are, and these center around an idea known as region of interest. So what you want to do is you want to be able to come to this problem, being able to kind of already be able to establish what the regions of interest are in any one image. You want to be able to sort of propose that, or have a way of proposing that, so you're not just trying every single bounding box of every single size in every single location. And early on in doing this, there was basically a pre-processing step that was done before you even started the training task, and that was for each one of these images, sort of in a non neural network training way, use the statistics of the pixels, kind of correlations in the pixels, what's called here lobby, to kind of already suggest where the regions might be. And then you pick again, a hyperparameter here, but you pick a certain number. You want to propose, in this case, the 2,000 regions in an image that are most likely to contain an object. And then use those to do your task, rather than the orders of magnitude more possible regions you could have tried. So it's like an a priori kind of, it's a step you take to sort of give this kind of prior to the network, saying, okay, well, these are the regions that you want to check out. Okay, so that's one of those steps here. Can anybody see a challenge that we're going to face doing this? If now what we want to do is classify what's in those boxes.
Box could have two things in it.
Say it again.
Box could have two things in it.
Yeah, could have two things in it. Yep. What else? I mean, in general, the quality of the boxes might not be awesome, right? So there's that issue. What other issues are there going to be?
The sizes are all different.
Yeah, the sizes are all different. So what's been the case so far when we are learning to classify the ImageNet images? We always had to do some sort of reshaping to make them, to fit them into the input dimensions for the network, right? The network only accepts whatever you've chosen to be the input dimensions. And for ImageNet, the kind of the standard, although kind of odd, is this 224 by 224. And all these regions are going to be at different sizes, so we're going to have to do some sort of like reshaping. But there's like vastly different sizes, right? Like there's huge regions, there's small regions, and so this might cause a problem. Any other ideas?
What about like situations where the objects are different sizes in the image?
Yeah, it's sort of related to this, the same question, right? Like you're trying to train a network that's going to be able to recognize objects that are large relative to the size of the image and small at the same time. So like there's a kind of challenge there. That's again, it's related to this thing of like the proposed regions are going to be vastly different sizes. Okay, so how do we go about doing this? Well, so the first really kind of successful model in this area is called RCNN, where R stands for like region proposal. Okay, so we're gonna kind of build up how this works as a network. So you take your input image and you first run this like offline region of interest proposal algorithm that's going to give you, roughly 2,000, or you pick it to be 2,000 regions. Okay, and then you're going to have to resize all of these so that they're all at the same size. What that size ought to be is again like another choice in the architecture here. But it might often be determined by like what network comes next. If you're going to use something like, a pre-trained ImageNet model, like these are going to have to be 224 by 224. And you might have some issues because of there being like some massive changes in scale due to some of these regions being huge and some of these regions being small. But in RCNN, sort of didn't deal with this. You'll see in other iterations they do deal with this. But you resize these images, and then each one of these is forwarded through the very same convolutional network. So these are all the same networks. Just each one of these independently, is going to be forwarded through some convolutional network. Then you're going to have your two losses here, right? This RCNN used an SVM, or this like hinge loss we learned way back when to do this kind of classification task for the objects in this in these proposed regions. And then of course you're going to have the regression task for the bounding boxes. So we're going to learn that. We're going to learn the bounding box determined by the ROI, the region of interest proposal mechanism. And we'll do we'll combine those. We'll have a hyperparameter that we learn or that we tune, and we hope that this all works really well. And as a first network kind of along these lines, like it actually works quite well. But there are a number of problems here that we've already discussed. So lots of funny things going on here. So you might start with, so like the way this was actually done was you start with like a pre-trained model and then use that to sort of fine tune, so like train on the ImageNet to fine tune that to do the classification part. And then after that's done, you're going to post hoc do to do both of these tasks right here. So there's like this kind of funny fine tuning. I don't want to get the details up because you're never going to do it. But then once that was done, then okay, now we're in this part where we can do like a full training of, adding this hinge loss in and then these regressions in. And, it sort of worked. The training was quite slow, and this was taking 84 hours on, like a single GPU. Obviously, this takes a lot of disk space if you're, what you're doing is like, to be fast, like creating all of these, like these 2,000 proposed regions, like these images on disk, so you can quickly read them up. And then, of course, inference was like super slow here as well, because you're going to have to run the the image proposals on each of these images in your test set that you haven't already run. And yeah, like it's just, like while while it worked, it has these problems. So then what happened was, like what happened a lot of these kinds of tasks is that people quickly iterated on these ideas. And so the next really kind of good idea here that made quite a lot of progress is what's known as fast RCNN. So as you might imagine, because it's called RCNN, it's got a lot of the same aspects of because it's called fast RCNN, it's going to have a lot of the same aspects as RCNN, but it's going to be, guess what, faster. And what do? Well, here's the first thing. So they deal with this like this thing that we discussed where the proposed regions are going to be like vastly different sizes. They dealt with this in a kind of an interesting way. They first took a pre-trained network and then forward this whole thing through, forward this image through the network to some feature map, like a Conv5 layer in a VGG, for instance. And this is a feature map, so it's got spatial extent, it's got channels, and they do the region proposal here on this kind of abstract feature map rather than on the original image, which is kind of interesting, right? Like maybe a little bit surprising that it would actually work, but it does, because like in VGGs, when you do this kind of region, or when you can do these convolutions, there's a lot of you're mixing kind of spatially the information, but if you haven't gone through too many layers, you haven't mixed it a ton, so there's still a lot of correlation between the original image and the feature map of this layer. So you do the proposals there, right? So we still are using like the same algorithm here, but on like something that's much smaller spatially, and you have like more consistent sizes for the regions as a result. And then instead of doing this like this like kind of naive resizing of those regions to the size that's going to be accepted by the next convolutional layer, you do this idea of what was called ROI, so region of interest pooling layer. And this is maybe a somewhat complicated slide, but the basic idea here is that once you have your region, again, like you're actually doing this at like a Conv5 layer. So instead of this being maybe like, remember this is not at the original resolution, but at this like kind of funny abstract resolution. What you're going to do is like wherever that region is proposed, you're actually going to split it up into a 7x7 grid, and whatever the size is here. So like in this case it's like 20 by 15, but this could have been something much larger. Whatever the sizes are, you're gonna basically split it up into a 7x7 grid, and you're gonna do max pooling. So like there's gonna be kind of a variable number of pixels that fit into each of these grid points in your 7x7 grid, depending on the original size of the region on that Conv5 layer. But you're going to do max pooling there, so now what you have is you have the 7x7 fixed size feature map that is now going to be the input to the next like convolutional network. So instead of it being this like naive resizing of the like in the original pixel space, you're doing this like this kind of standardized max pooling, but like the actual, if you think about like what the pool sizes are, they're variable depending on whatever this original size was. Questions about that? It's a little bit complicated, yeah.
It's still unclear to me how the region of interest is obtained. Like
it's done in the same way that was done in the previous just in RCNN. The same kind of like statistical.
Would they get the range of interest out of the original image, or they?
No, they did it it's done at this more abstract layer. You can look at the receptive fields of what's in here, and you can infer where that region of interest is on the original image. But the proposal, like the algorithm, is run, in this kind of abstract feature space with a smaller spatial extent for the feature map. So it runs a lot faster.
Oh, so is it differentiable though? Is it out of?
No, it's not. Like you're right. You're not back propagating through that operation. So it's not like totally end to end. Is what you're pointing out. It's great because you're going to see the next iterations are going to build in that like kind of end to end capability. But yeah, you're right. Like, those aren't differentiable. Those are done like offline, not part of the train.
So they use a trained VGT to get the first stage, right?
Yeah. So you take something that was already pre-trained to get you this representation here. Do your ROI proposals there. Do this kind of this like max pooling to get a fixed size to turn like this variable sized feature map into a fixed size one, and then that will go into the next stages of the network where you are going to start to learn parameters.
So we only back propagate to that stage, right? To the stage.
Yeah, watch. I have a picture here from the paper that will.
Okay, thank you.
That'll help. Yeah. Right. So you do all that. And then, because that was done small enough, you go directly to the next stage of the network, which in fast RCNN was to go straight to fully connected layers. So like, extending the that feature map, like basically, like vectorizing it and then doing these fully connected layers. And then that will feed into these heads, right? To do your bounding box regression, to do your classification. Okay, the green arrows are all pointing like in the forward direction, right? Where these things are going. And then you're going to combine those two together to give you your single multitask loss. Again, combined with some hyperparameter expressing the balance between the two losses. Right, and so then we're going to back propagate. We're going to back propagate through what we can here, like what learned parts we can, and yeah. So what's nice about this is that it really speeds things up. So if you look at the training times, there's this SPPP net that's here, that's part of this paper that we didn't talk about. It's a small extension of the RCNN to kind of deal with some aspects of the region proposals that made it faster. But the important part here is that training this is a lot faster, and importantly, at inference, but the test time when we want to draw the bounding boxes and classify what's in them for test images, this has gotten way faster. Going from this 49.47 seconds to 2.3 or 0.32, and the difference between the blue and the red here is the blue includes the region proposal time. Right, it's like running that algorithm in between. The red does not. So what you can see is there's like consistently a 2-second hit that we take when we have to do the region proposals. I think it was a question. Yeah.
What are the accuracies compare?
Say it again. Oh, like how do they compare to like ImageNet?
Or to each other, like how does RCNN's accuracy compare to?
Yeah, so like these are all roughly the same at this point. Yeah. Right. It's just the time it's taking to to do this. So we got things really quite fast, orders of magnitude faster, but we're really you can see now like at this speed, the bottleneck really is the region proposal, right? Like if we want to make this faster, if we want to make this better, we're gonna have to fix that. So that's what happens next in like subsequent years. Guess what it's called? We have RCNN, we have fast RCNN, and the next like popular iteration is called
Faster.
it's called faster RCNN. So basically, what faster RCNN does is like kind of does the inevitable, which is that it has an additional part of the network that is doing the region proposals. It does this in kind of a funky way. So this is similar to fast RCNN in that there's some neural network that's going to produce a feature map, and we're going to do the region proposals in that abstract feature map rather than on the original image. So that's all the same. We're going to propose regions, but instead of there being this kind of offline algorithm to do it, we're going to learn how to do it. And the learning here is a little bit complicated, like like how it works. But basically, there's at each pixel you're going to have it's thought of as an anchor. There's like 9. Well, it's a hyperparameter, but there's a certain number of like basic sized regions that are tried at each of these anchors. And you learn a classification problem on top of this. That's what this like classification loss is. It's basically like, is there an object in this bounding box or not? And then you learn to do the regression there. If the network thinks there is an object, then those proposals are passed forward into the same kind of ROI pooling layer that we just saw in terms of like going from these variable-sized feature maps to a fixed like 7x7 size feature map through maps pooling, and then you do your classification and bounding box regression loss with those regions. So this these are losses on the region proposal network. And the classification here is not the same as there. This is really like binary object or no object. This is the same though as just like predicting the regression. And I think when this was first being done, this was trained. The region proposal network was trained kind of in this alternating way where you would like train the region proposal network first, and then you train this, and then you could. Now this has gotten a lot better. You train this again, and you kind of keep going back and forth. Then it was like just done in an end-to-end way, and seemed to do just as well. And so the typical if you were to train something now with faster RCNN, you train all this all at once. There are some additional tricks. Part of the problem of training it all at once is that sometimes these region proposals they can especially early on in training can be quite correlated. So it's taking a long time for the network to convert, to learn to convergence because there's so many correlated outputs that you're learning here. So while you're spending a lot of capacity learning, you're not learning a whole lot of new information because the correlation's there. So you can add some tricks in there to separate those out, and then you get kind of what's the faster RCNN today, and it's trained with all 4 of these losses all together. Again, with some balance between the losses. Yeah, go ahead.
How do we get the crowd truth for the first classification loss?
Right. So somebody has to. It has to be.
But it's
it has
just
to be
a
provided.
feature map, right? It's very abstract. So how can people label it?
Well, what the objects are here in the original image, and where they would map to in the feature map.
So they just resize it, kind of.
Yeah, something like that. It's a good question. It's actually there's a lot of pieces to keep track of. This is now very, very complicated compared to just the straightforward classifications that we were doing just on ImageNet, right? So and it's a great call out that there needs to be labeled data to be able to do these, and that it's not. It's kind of funny because it's happening in these abstract spaces, but because you can do it in the original image space, you can easily kind of propagate that to whatever convolution layer you're using.
So another question. So we have
Yeah.
two levels of losses. So how do we calculate the gradients at the lower?
Yeah, so like so the whole like the whole loss everything's combined. But remember, like when you take these gradients, like you're going to take a gradient of so there's going to be some weights in this that are further ahead in the network beyond these right here, right? So these are going to be constant with respect to the parameters of those for those losses, like for those parameters. So when you start taking these gradients, these partial derivatives with respect to those losses, these losses are zero. Like there's no contribution. But for parameters that are further down in the network where all the losses are contributing, then every single one of those loss terms is going to contribute something to the gradient, and so they all are contributing signal. Right? So it's just a much more complicated computation graph, but if you just follow all the rules, do your automatic differentiation, when you compute the gradient or the partial derivative of these losses with respect to say like a parameter in this network here, it's going to take signal from all four of these. When it's above these losses here, like above these heads, so like beyond this arrow here, when you take those partial derivatives with respect to those parameters, only those two losses are going to affect it because these are like
so that's
behind it.
The bottom part is kind of a combination for losses.
Yeah.
So how do you do the ROI pool? So you get a whole bunch of little boxes everywhere.
Yeah. So I mean, I sort of tried to describe it a little bit without getting into too many details. It's a little bit complicated, but basically each pixel, it's called an anchor in the literature. But you can think of it as an anchor. There's it's a hyperparameter, but there's like typically 9 bounding boxes that you're going to try at that point of a certain size, and that's going to propose. Within those regions, you're going to do this classification. Is there an object in this or not? If there is, then you're going to regress the bounding box starting from the proposed region, but to the actual bounding box that contains that object, like in the actual labeled training data. So it's like a refinement of that bounding box rather than like a full regression like we were doing in what we do at the top there in that loss up above, which is like what we were doing in the fast RCNN and the RCNN.
So we're kind of like guessing where the bounding box is, and then
We're basically like taking a good guess of where they are, and then regressing, and then like adjusting from those proposed anchors to the actual bounding box. So like the signal is, there's no object here, don't worry. Then like, oh, there's an object here. Okay, cool. So like now let's try to refine this proposal to something that's actually, more accurately the correct bounding box. And then that gets this part of the network that proposes those working. And then when you're running like inference, you're using that classification loss to decide which of these proposed regions actually gets propagated through to the rest of the network, where you actually would do the full classification loss, like for the objects in there.
how much faster?
That much faster. Right there.
Can you put it on a log scale, all of them?
What's happening?
It seems like they're cutting by like about 10 times each time.
Yeah, something like that. I mean that's SPP net, but yeah, just if you ignore that, then yeah, like basically like the RCNN, the fast RCNN, just like reduce this problem to basically the speed of the offline region proposal algorithm, and then when you get rid of that and learn it end to end, then you get this much you get the speed up. So this is just all neural network at this point. There's no like offline algorithm that is creating additional time at inference time. Cool. So anyways, like that's some of the like the history of how that's gone. There's additional. There are. I'll talk about it in just a second. Yeah. So there are additional kinds of these object detection algorithms that are like faster CNN. I'll just talk about a few of them here in a second. One thing I wanted to point out here was Mascara Cnn. So Mascara Cnn basically is faster RCNN, but it has this additional head that that predicts, like it's basically like, yeah, it's predicting the mask. So like which pixels, this is now at like, at this like more abstract feature map, but which pixels in that feature map are actually like the object, correspond to the actual object within that bounding box, within that region. So it just has one more head where again for each of the pixels in that mask, and for each of the classes, it's basically saying which pixel is part of this object, which is not. If it's the incorrect object, the mask is going to have nothing there. But for the correct object there, you're going to have a mask. You're going to learn the correct mask. And so this is a way of now doing the instance segmentation, just like directly on top of the object detection. You just use exactly the same network. You just add one more loss that's going to learn the pixel mask that's going to correspond to which pixels correspond to the actual object. And again, you have to have your data has to have these kinds of masks in them to be able to learn this. So so mask RCNN, so this faster RCNN with this mask, this additional mask loss, works super well, right? So these are examples of this. It's still very popular today, although there's a few others I'm just about to talk about that you might have heard of, and you'll see different versions of. But so it's doing the object detection, drawing the bounding box, saying, you can't really see it here, but this is saying what object is in there. So it's motorcycle, person. But then it's also, with the mask part, it's telling you which pixels within that bounding box are part of the object. So again, an all learned end-to-end, which is very, very cool. You can use this to do a variety of interesting things like this pose estimation. Again, you need the labeled data to do this kind of thing. You can see how this would work, right? It's like you're basically saying which pixels within that mask correspond to which, joints for estimating the pose of usually people, but you can estimate the pose of various things as long as you have the labeled data. There are ways of doing this without proposals. So you might have heard of YOLO networks. There's actually, I think it's up to version 5 these days. It stands for you only look once, not you only live once, but you only look once. And the idea here is kind of similar to what we were just talking about with how the region proposal network works. But you're going to have these kind of predetermined bounding boxes, and you're going to for each of those you're going to decide if there's an object in there or not. Basically, this is done through a kind of confidence measure, and then for those things that it thinks it has an object in, you're going to do exactly the same thing where you're going to regress the box to the actual box that contains that object. So this is very much the same as that, but it's kind of doing this directly without there being any region proposal network. Just start with this idea of these base boxes and learn to do that task.
Has anyone tried to just pull it off with just convolutions? Or trying to do the bounding box and the classification with just convolutions?
Meaning that like you would draw the you would your label would be the convolution. Let's see, you're saying like there would be a mask that would show you the bounding box? I don't think so. I don't think I've ever seen that. It's a lot of additional computation just to get 4 parameters. Yeah. But I wouldn't be surprised if it's been tried. I mean, there might be a paper out there. Might be a lot of papers, I don't know. Definitely not what you see for these tasks. Like you'll see faster RCNN, you see various types of YOLO. This SSD is something similar, single shot multi-box detector. Similar idea to the YOLO. Okay. So, yeah. So where are we? Okay. So, yeah, so one of the things that you might have, I mentioned a couple times, is that to do this, there's this got pretty complicated pretty fast. There's a lot of decisions to make. There's a lot, like what does your backbone look like? What kind of object detection architecture you're going to do? Like, how are you going to do the region proposals? There's a lot of there's a lot of losses. How are you going to balance those? How are you going to choose how to balance those? This is really to do this well. You need to have really good data. Like, where does that data, come from? Like, there are fortunately some data sets out there that are used for this kind of thing that have this. But like in general, if you're going to do this for your own, your own application that isn't very similar to the data sets that already exist, you're going to have to do a whole bunch of labeling of this data. That's quite expensive. So it's quite challenging. But nevertheless, this is probably one of the most used applications of neural networks in computer vision to do this kind of instance segmentation. For instance, in your self-driving cars, this is a really important step in determining at any frame, any moment of driving, what are all the objects out there? What are they? Importantly, is that a stoplight? Is it green? Is it yellow? Is it red? Is that another car? Is that a human being? Is that a bunch of human beings? I mean, there's just these are really important inputs to something like that to be able then to do the next step of learning, which is what decision do I make about this instance of driving given the state of the world? But again, the state of the world is described by all the objects and their locations, in my field of view.
For videos, is the time dimension playable, or is
Mm-hmm.
it just?
Yeah, in videos. Videos are you can do all of this kind of in very much the same way. You'll have I mean you can think of you can approach all of this in very much the same way, but instead of using 2-dimensional convolutions, you would use 3-dimensional convolutions. So you have some way of kind of extending the notion of convolution into time in some.
Like a 3D image almost?
Yeah, exactly.
Rectangle.
Yeah, I mean, again, so your tensors, so your feature maps, instead of them being tensors of order 3, they're going to be tensors of order 4, right? So, I mean, it's just all the ideas kind of, apply just up one order in the tensor. And there's a lot of ideas about how to make this efficient, and you can imagine what some of those might be. But in general, all these ideas kind of easily extend to higher dimensions, higher orders of the input tensors. Yeah.
It seems to me that the training of faster RCNN relies on how good the region of interest algorithm is, right? So
Yeah.
I'm just wondering, currently, what is performance of the region of interest algorithm? Does it predict very accurately?
I don't really know the details on how good it is. I just know that it powered RCNN and fast RCNN in such a way that it allowed that whole algorithm to work well, like to be able to take an image and be able to draw appropriate bounding boxes and classify those. So I've never seen anything that's like assessing the performance of it. Just like the way that it works well enough to power the application. Yep. There were other competitions going on at the same time as the image classification competition that were specifically for object detection, that were that used different kinds of data sets. And again, you can see like around that same time, so like 2012, AlexNet wins the classification competition, and you can see in 2013 you now have the like things like RCNN competing to do these tests and like starting to really make massive improvements here. This is a mean average precision. It's a type of classification measurement, but you can higher is better. So you can see that these are quickly getting better year after year. So again, the effect of deep learning on this task. And then I just have this in this, you don't need to write this down, but if you go look at the slides on Canvas and you go look at this link, this is a really cool tutorial on like doing instant segmentation. That's you can do in a laboratory notebook. So would encourage you to check that out. It's pretty fun. Okay, that's it for today.
Has anyone tried to do like a Where's Waldo with this kind of?
Yeah, definitely.